Hi, everyone, and welcome to part 2 of the lecture on alpha carbon chemistry. We left off at the beginning of chapter 21, section 4, called Klein condensations. And it's important to note that in the previous section, we were talking about aldol condensations, and those used aldehydes and ketones to undergo reversible condensation reactions. And this section is about the fact that esters can also undergo reversible condensation reactions. And when you use an ester as your reactant, instead of being called an aldol condensation, it's called a Klein condensation. And the reaction involves two esters, actually, so 2 moles of this, being reacted to form what's called a beta ketoester product. The reagents involve first treatment with a base, and the base will be a alkoxide base that matches the ester. Right? So when you're using an ethyl ester, you'll use sodium ethoxide. If you were using a methyl ester, you would use sodium methoxide, and so on. And we also need an acidic workup to isolate a neutral product. The The reaction is essentially just a nucleophilic acyl substitution where the nucleophile is the enolate formed from an ester. And we've been talking in this chapter a lot about enolates as reactive intermediates. And the electrophile is the same ester, right, that the enolate is formed from. So essentially, we're using 2 of these. One of these forms an enolate and then reacts with another of the same ester to form the beta ketoester product. Okay, so let's talk about the mechanism. We talked about the fact that it's going to go through an enolate intermediate. And so the first step is going to be formation of that enolate. So our base, and again, this is the matched alkoxide to the ester, will take in proton through proton transfer from the alpha carbon of the ester. And you might ask yourself, can this alkoxide also act as a nucleophile instead of a base and do a nucleophilic attack on the carbonyl carbon? And the answer is yes. However, after that happens, there will be a loss of a leaving group, and there are 2 leaving groups, and they're identical, right? And that would be the alkoxide leaving group. So even though it can do a nucleophilic attack, essentially it gets kicked right back out. And eventually it may act as a base instead of a nucleophile and deprotonate the alpha carbon. Once we form the enolate, the carbon that has a partial negative charge will then do a nucleophilic attack on another ester, specifically the carbonyl carbon of another ester. So we have a nucleophilic attack, a resonance arrow to move electrons up to the oxygen in order to avoid exceeding the octet on this carbon. That gets us to this intermediate, which has a negatively charged oxygen. If it reforms the carbonyl, it needs to kick something out as a leaving group, and the alkoxide can act as a leaving group in this reaction. So we can go ahead and do loss of a leaving group with this resonance arrow, generating a ketone here. Now notice that now we have a 1,3 dicarbonyl, right? One of the carbonyls is a ketone, the other is an ester, but regardless, we have a 1,3 dicarbonyl. And we talked before about the acidity of the hydrogens that are on the alpha carbon in between the 2 carbonyls. They're more acidic than typical alpha carbons, right? And they're more in the range of 9 to 10 in terms of pKa. And we're under basic conditions with our alkoxide. So there will be a proton transfer that will highly favor the products. And this is essentially what's called the driving force, or the step that drives the equilibrium forward to form the product. So this is a very important step where we do this proton transfer. It's very favorable with the difference in pKa. Right? Again, the pKa of the acid is about 9 to 10. The pKa of the alcohol, which is the conjugate acid, is about 16 to 17. So that's a strong enough difference in pKa where the reaction will be very product favored. So we don't want to isolate this because this is not neutral. So that's where the acidic workup comes in. At the end of the reaction, we need to do an acidic workup, which will reprotonate the alpha carbon and giving us this neutral beta keto ester product. Okay, it's important to note that there are some limitations to the Claisen condensation. The first is that the starting ester must have at least 2 alpha protons because we need to remove one of them in the first step to form the enolate, and we need to remove the second one in the penultimate step, right, where the alkoxide removes one of the protons that is in between the 2 carbonyls. That's the step that drives the equilibrium forward. So that's a very important step as well. So there needs to be at least 2 alpha protons on that starting ester for the reaction to take place. The second limitation is we cannot use hydroxide as the base, because if we use hydroxide as the base, it will do a basic hydrolysis of the ester, yielding the carboxylate, which is not what we're trying to do. We do not want to hydrolyze the ester in this reaction. So we saw this basic hydrolysis of the ester in the last chapter, right? And this would be an undesired reaction. We do not want to hydrolyze the ester. The third limitation is that we do need to use the matched alkoxide, right? So if this is an ethyl group, then the base that we use must be sodium ethoxide instead of sodium methoxide, for example. And the reason for that is to avoid transesterification. We talked about the fact that the base that's used can act as both a base and a nucleophile, right? Because, for example, methoxide is considered both a strong base and a strong nucleophile. So if it doesn't act as a base and instead acts as a nucleophile, then it can do a nucleophilic attack on the carbonyl of the ester. And if ethoxide gets kicked out instead of methoxide, then we've essentially done what's called a transesterification and converted the ethyl ester to a methyl ester. Because that won't likely occur 100% of the time, at the end you're likely to get a mixture. And organic chemists always want to avoid a mixture. So it is important to not use hydroxide and to not use any other alkoxide other than the one where the alkyl group attached to the oxygen matches in terms of the base. Okay, just like in aldol condensation, we can also do a crossed Claisen condensation. So recall, we talked about doing crossed aldol reactions previously, and they're challenged because if you don't use careful consideration of the right conditions, you can end up with a complex mixture of products. The same would be true for our Claisen condensation. So if you don't want to get a mixture, you instead only want to get one product, then the following criteria must be met. The first one is that one of the esters cannot contain any alpha protons. So notice this is a benzylic ester, and the alpha carbon here does not have any hydrogens attached to it. That's going to be super important because this ester cannot form the enolate, right? And so only the other ester can form the enolate and proceed with the reaction. So that is a helpful limitation for doing a successful crossed Claisen condensation reaction. The other thing we can do is perform what's called a directed Claisen condensation, where instead of using the matched alkoxide, we can use LDA as the base. So the way this works is very similar to the aldol reaction. We take one of our esters that contains the alpha carbon with hydrogens attached. At low temperature, we will treat this with LDA, which again is lithium diisopropylamide. It's a strong, bulky base. It will deprotonate the alpha position to form the enolate. And then at that same low temperature, dropwise, we would add in the second ester. And in this case, we don't have to have an ester without alpha protons. It can have alpha protons if we use LDA. because at low temperature, it turns out that the nucleophilic attack that's desired will be faster than the deprotonation of the alpha position of the second ester that's being added. So again, the enolate can act as both a nucleophile and a base. And luckily, it will, at low temperature, prefer to do nucleophilic attack than proton transfer. And we won't end up with a mixture of enolates in the solution. And we've successfully done a crossed aldol condensation. You might be asking yourself, how do I know if I need to do a regular Claisen condensation or a crossed Claisen condensation? And the answer is to look at the alkyl groups. Notice here that there's a phenyl group, right? And there is not one attached to this carbon. Right? Notice here that this carbon just has 2 hydrogens attached to it, right? But the other alpha carbon has an alkyl group. So these are not going to come from the same ester. We needed to use 2 different esters, right, in order to achieve this particular beta keto ester type products. And that's going to be the clue that you need to do a crossed Claisen condensation. Okay, let's talk about intramolecular Claisen condensations. You might recall also with the aldol condensation that we can do intramolecular aldol condensations. Those did not have their own name in terms of a named reaction, but we could still successfully perform intramolecular aldol condensations. And we can also successfully perform intramolecular Claisen condensations. When we do an intramolecular Claisen condensation, instead of calling it a Claisen, it is now called a Dieckmann cyclization. So notice that we are starting with 2 esters that are tied or tethered together in the same organic reactant. Treatment with a base will form an enolate, which will do a nucleophilic attack that's intramolecular. After loss of a leaving group and deprotonation by the base, we will need an acidic workup to reprotonate carbon number 2. Just like with the aldol condensation, intramolecular, the reaction prefers to form very stable rings, such as 5- and 6-membered rings. It may be possible to also form other sized rings, such as a 7-membered ring, but typically the highest yields are when we form either 5- or 6-membered rings. And if it's a 4- or 3-membered ring that's being formed, it's likely not going to be a successful reaction because of the ring strain associated with those rings. Okay, let's do a practice problem. Let's think about how we would draw the mechanism for the Dieckmann cyclization. So recall that this is simply just an intramolecular Claisen condensation. So we should do the same steps we would do in a Claisen condensation. Just in this case, we're going to be forming a ring. So go ahead and pause it and go ahead and try to draw out the reaction. Also, think about the fact that we do need an acidic workup, and don't forget to include that in your mechanism. Okay, let's go ahead and draw out the mechanism for the Dieckmann cyclization. I'm going to go ahead and add in some hydrogens on one of the alpha carbons. Notice that there's symmetry, rotational symmetry here. So we, both carbons 2 and what is labeled carbon number 5 are equivalent. So it doesn't matter which one you deprotonated. You can go ahead and add these hydrogens in and then draw out the base that we're going to be using as the reagent. Okay, so the first step is going to be proton transfer, where we form the enolate. Again, you can deliver your lone pair and negative charge to this carbon or go all the way up to the oxygen. It doesn't matter, and both mechanisms are correct. For simplicity, I am just going to put the lone pair on the alpha carbon. Okay, so now I'm going to draw the enolate. And again, I noted that I decided to deliver the lone pair onto the carbon instead of the oxygen, but it wouldn't have mattered if you had moved the electrons all the way up to the oxygen and had an oxygen with a negative charge. If you want to, you can continue with the numbering just to make sure you haven't accidentally added or left off any carbons. It's also not super important to change the orientation here. I just did so because it will make it easier to show the ring formation, but it's optional. So now that we have the enolate, which is our nucleophile, we can do a nucleophilic attack on the carbonyl carbon of the other ester. And make sure to show that resonance arrow, moving electrons up to the oxygen. Right, at any point, you can add in your labels. Right? So this is carbon number 1, carbon number 2, and then 3, 4, and 5 should all be methylenes. Right? And that makes this carbon number 6. So at carbon number 6, we have generated an oxygen with a negative charge. And we also have this ethoxide substituent as well that we can draw in. And I'm just going to go ahead and try to make sure I don't forget lone pairs as I'm drawing this mechanism. Okay, so now we have our alkoxide intermediate, and we can do loss of a leaving group where we can kick out this ethoxide. At this point, it will be very tempting to think that you're done because you have synthesized the product. However, this is not the end of the mechanism, because recall that now that we have a beta keto ester, the hydrogens on the alpha carbon interior to those two carbonyls are acidic, and we are under basic conditions. So we do need to show that final proton transfer. By the way, it is the reaction that is the most favored in terms of equilibrium, so it's the so-called driving force of the reaction. So in this case, if we draw reversible arrows for this particular mechanism, we'll show that this one is favored. Again, note that I just decided to deliver the lone pair to the alpha carbon, but you could have also moved the electrons all the way up to either one of the oxygens, and that would still be correct. So this is where we end the first step, and the acidic workup, the purpose of that is to protonate the alpha carbon. So I can go ahead and draw in some hydronium ion. And I sometimes draw it in different color just to illustrate to you the fact that it wasn't there from the beginning, right? This reaction is done under basic conditions, right, all the way until the final proton transfer. And that's the final proton transfer leading to the product. All right, let's go back to the slides. We're going to immediately do another practice problem. This practice problem is asking you to determine the reactants that will produce the following compounds via Claisen condensation and decide which base to use. You're either going to pick sodium ethoxide or LDA. Right? So the idea is think about the products here. They're both beta keto esters. Try to decide which carbon-carbon bond will be formed in this Claisen condensation, and then retrosynthetically move back to the reactants, and then in the forward direction provide the reactants to form those. And ask yourself, was it necessary to do a general Claisen condensation or a crossed Claisen condensation? Go ahead and pause the video and try the problems, and then we'll go over it. All right, let's go over these. Right, so I mentioned one reasonable way to think about this is to think about where the beta keto ester is. Right, so if this is the ester, right, then this would be the alpha carbon and the beta carbon. And it's important to note that the new carbon-carbon bond that's formed in the Claisen condensation is the carbon-carbon bond between the alpha and beta carbon in the product. Right? So we're going to just take note of the fact that we'll be making that particular carbon-carbon bond. Because the reactants are both esters, right, we need to convert this beta carbon into an ester as we are thinking retrosynthetically here. Right? So for sort of going backwards, right, we are going to simplify this to two esters. And it makes sense, since this is an ethyl ester, just to draw an ethyl ester. Again, this is the beta carbon. And then this side will have been the enolate, right, which starts off as just an ester. Right? And so if you draw that one in, right, and label the alpha carbon, then you might have noticed that the two esters that we generated are the same. Right? And so when they're the same, you can just do a typical Claisen condensation and not worry about the conditions necessary for a crossed Claisen condensation. So to draw out a typical Claisen condensation, we'll just draw out the ester once. Draw the arrow, right, that then produces the product. And then add in the reagents, right? And the reagents are, for a typical Claisen condensation, we would just use the matched alkoxide. So step one, sodium ethoxide. And then step two, we don't want to forget about the acidic workup. That's always necessary. Okay, let's look at the other one over here. So again, this is our ketone, right? And this is an ester. So I can label this the alpha carbon of the ester and the beta carbon for the ester. Think about making the carbon-carbon bond between the alpha and beta carbon. So when we simplify this through retrosynthetic analysis, a weird arrow, sorry about that. We are going to simplify this to a, so this ester, where this is the beta carbon, right? And again, I just chose the same one as here just for simplicity. And because I don't want any transesterification, it's ideal to use the same R group. So, and then the enolate will have come from the alpha carbon side, right, which just comes from a more simple acetate ester. So notice now that the two esters are not the same. Right? So in this case, we do need to perform a Frost-Claisen condensation. So the idea behind a Frost-Claisen condensation is to start with the ester that's going to form the enolate, which is this one. Draw that one in. And then ask yourself, does the other ester have an alpha hydrogen? And the answer is yes, right? This would be the alpha carbon to this particular ester, and it does have one hydrogen here. So we're not able to use sodium ethoxide with the first strategy for Frost-Claisen condensations. Instead, we need to use LDA and use the second strategy because both esters have an alpha hydrogen. So it is best then to just sketch in the product first and then worry about the reagents. We're going to use LDA. Right? And even though this is done typically at a very cold temperature, the book doesn't put that information over the arrow, so I'll just go ahead and leave that out. Followed by dropwise addition of the second ester. And an acidic workup. And that will be a successful Frost-Claisen. All right, going back to the slides, we're going to move on to section 21.5 called alkylation of the alpha position. So note that when we have, for example, a ketone that has protons at the alpha position, recall that those are acidic and that when treated with a strong base, they will be deprotonated to form the enolate. That enolate is nucleophilic, and one of the reactions it can do is react with an alkyl halide as an electrophile. It is going to do an SN2 reaction. Here it shows the mechanism from the enolate doing the SN2 reaction on the alkyl halide. So recall that with SN2 reactions, it's important to have unhindered alkyl halides. So this alkyl halide is most preferably either a methyl halide or a primary alkyl halide. The secondary or tertiary alkyl halides, the major mechanism that will occur is an E2 reaction, which will not provide the product that we want. It's also important to note that enolates of aldehydes and ketones undergo the aldol reaction if there is still some aldehyde or ketone present because of the choice of using, for example, sodium hydroxide instead of a stronger base. So in the alkylation of the alpha position reaction, we do need to use a stronger base, such as LDA, that will completely form the enolate from the reactant, such that no electrophile is still present, and that will shut down any possible competing aldol reaction. Another issue with the alkylation reaction is regioselectivity. So recall that regioselectivity means that it's possible to form more than one constitutional isomer in a reaction, and we want to favor one constitutional isomer over the other through appropriate reaction conditions. So specifically, we need to consider regioselectivity when we're using an unsymmetrical ketone, because when you use an unsymmetrical ketone, two different enolates can form. Recall that aldehydes only have one alpha carbon with hydrogens attached, so it's not possible to form more than one enolate from an aldehyde. But two different enolates can form from a ketone, particularly unsymmetrical ketone. Okay? So it's important to consider regioselectivity when you're using unsymmetrical. So let's look at this ketone, for example. Notice it is not symmetrical because of this alkyl group that's already present on the cyclohexanone. And if we treat this ketone with a strong base, that strong base might deprotonate the more sterically hindered hydrogen on the right, leading to this enolate, or it might deprotonate one of the two less sterically hindered hydrogens on the left, leading to a separate enolate. So we have the possibility of forming more than one enolate with asymmetrical ketones, and which means that there might be a mixture of products that results from alkylation of the two different alpha carbons. Luckily, there are conditions that we can use to favor either enolate, depending on which one that we want. So the more substituted alkene is the more stable enolate, and so we're going to call that the thermodynamic enolate. And the kinetic enolate then is the enolate where deprotonation has occurred on one of the less sterically hindered hydrogens. Because they're less sterically hindered, there'll be less steric hindrance in the transition state, which will be lower energy, leading to this enolate compared to this. So this enolate is not as substituted, so it's not as stable. However, it does form faster. So we can take advantage of that by using conditions that favor kinetics versus thermodynamics. So the appropriate choice of base, right, will determine whether the kinetic enolate or the thermodynamic enolate forms as the major intermediate in this reaction. Notice that the kinetic enolate goes through a lower energy transition state. And again, that's because of less steric hindrance in the transition state, leading to the deprotonation of one of the less sterically hindered and more accessible hydrogens on the alpha carbon here on the left. So regardless of the base, right, the major enolate initially will be the kinetic enolate. However, at higher temperature, it's possible for the two enolates to form an equilibrium directly through deprotonation of each other's alpha position. So basically, the equilibrium is formed when this enolate acts as a base, right, to take the proton of the opposite alpha carbon to then form the other enolate. So this reaction, just to clarify, this reaction is not, this particular step is not thought to be reversible, because again, we're going to be using a strong base to avoid the competing aldol condensation, a strong base such as sodium hydride or LDA. And if you recall, when we use sodium hydride or LDA, we don't form an equilibrium between the reactants and the products because of the huge pKa difference between the acid and the conjugate acid. So those proton transfers with LDA and sodium hydride are irreversible. So, but we can still lead to the formation of the thermodynamic enolate at higher temperature because of possible equilibration between the two enolates directly, right, without going back and then going forward again. So in order to form the kinetic enolate, we want to have less energy available such that the kinetic enolate is trapped and the equilibration between the two enolates is not possible. And then in order to form the thermodynamic enolate as the major enolate in solution, we want to do the reaction at a higher temperature such that there will be an equilibration between the two enolates, and the more stable enolate will then be the major enolate. So we want to take advantage of temperature, but we can also take advantage of the choice of the strong base. Recall that sodium hydride is a small, strong base, and LDA is a strong, bulky base. And so just the initial proton transfer using LDA will favor the less sterically hindered protons, and using sodium hydride will favor the formation of the more stable enolate because it's not bulky and there'll be less steric hindrance in the transition state. Okay, so again, if you want to favor the kinetic enolate, use the conditions in the first step of LDA at -78. And if you want to favor the thermodynamic enolate, you're going to use sodium hydride at room temperature, followed by whatever alkyl halide you choose. Of course, remember that it's most preferably methyl or primary in order to do the alkylation at the alpha carbon, right, that is desired for your reaction. Okay, let's go ahead and take a break to do a practice problem. This is a two-step synthetic sequence where you're asked to generate the products in each step. Take careful note of the base and the alkyl halide to draw the products of the reactions. Go ahead and pause it and try the problems, and then we'll go over it. Okay, so let's go ahead and go over the practice problem. So notice that this is a symmetrical ketone. Right? So we are going to be forming an enolate with our strong bulky base LDA, but there is going to be no worry of regioselectivity because of the symmetry here. So forming the enolate on either side is equivalent, and then we'll do an SN2 reaction to add this ethyl group to one of those alpha carbons. So it doesn't matter if you put the ethyl group on the left or the right. Again, I'm just going to go ahead and add it here. Right. At this point, now we do not have a symmetrical ketone anymore. Now it is an asymmetric ketone, which means that there are two alpha carbons, one on each side of this ketone, and they both have at least one hydrogen attached to them. So we have to carefully think about which proton would be removed using our strong bulky base. Recall that because it's bulky, it will be able to access the less sterically hindered hydrogens on the left through a lower energy transition state. So we're going to form the less stable kinetic enolate, where the anion and negative charge are on this alpha carbon, and then do an alkylation reaction where we add a methyl group on that carbon. This one, it is important that you add that methyl group to the carbon, the alpha carbon on the left. Okay, let's go ahead and go back to the slides. Going. Let's do another practice problem. In this case, we're going to be doing a multi-step synthesis. So we're going to be thinking about how we can string reactions together to go from this reactant to this product. And go ahead and pause it and think about the reactions that you might want to use and your best, and then we'll go. Okay, let's go ahead and go over how to do this problem. So the first thing is we are thinking about alkylating the alpha position, right? And so I noticed that I added an additional methyl group, right, to this carbon. But right now, because of the fact that it is an alcohol and not a carbonyl, right, this is not the alpha position to, for example, a ketone to be able to do this alkylation. However, recall that secondary alcohols and ketones are related through a redox sequence. So we can oxidize secondary alcohols to ketones, and then later on we can reduce it back to the secondary alcohol. So I'm thinking that if we do an oxidation, right, that might be a good first step in this synthesis. Then we can think about the fact that there are alpha carbons on this ketone, and we can selectively alkylate the alpha carbon on the left using the appropriate conditions to introduce another methyl group. So that's going to be our next goal. And then because the product doesn't have a carbonyl, we want to go ahead and reduce it back to a secondary alcohol. So notice that I've just drawn out my synthetic pathway without drawing in any reagents at first. That's one strategy that you can use that might help you figure out the path that you want to use. Okay, so the first goal was to oxidize the secondary alcohol to a ketone. We can do that using either PCC or sodium dichromate. And then the alkylation, we need to be very careful because we don't want to add the methyl group to the alpha carbon on the right. We do want to add it to the alpha carbon on the left. This is the more sterically hindered alpha carbon, and it will go through the more stable enolate. So the appropriate conditions to choose the thermodynamic enolate are sodium hydride at room temperature, followed by the introduction of the alkyl halide of our choice. You can use methyl chloride, bromide, or iodide. And then we want to reduce that ketone back to a secondary alcohol. And we can do that with either sodium borohydride or lithium aluminum hydride. Okay, let's go back to the slides. And we're going to be now continuing with alkylation at the alpha position, but we are going to be talking about a reaction that converts an alkyl halide to a carboxylic acid. Notice that we are going to be forming a new carbon-carbon bond, and we are going to be adding 2 additional carbons, right, and doing the functional group conversion of an alkyl halide to a carboxylic acid. So those are all important parts of this reaction. The reaction is called the malonic ester synthesis, and it's called that because the organic reactant that provides these 2 carbons is diethylmalonate. Okay, so diethylmalonate is this diester that contains an alpha carbon in the center with particularly acidic hydrogens. We call that hydrogens attached to alpha carbons between 2 carbonyls are more acidic with a pKa of more like around 9 to 10, depending on the exact substrate. So this is a great substrate for proton transfer, right? A base like sodium ethoxide will deprotonate the alpha position to form the doubly resonance stabilized enolate. So you can think of this as, of course, it's a nucleophile, right? But it's a more stabilized nucleophile or a weaker nucleophile. But even though it's not as reactive as nucleophiles or other enolates, right, that are not doubly stabilized, it is still nucleophilic, and it can do an SN2 reaction on an alkyl halide. Of course, because this is an SN2 reaction, you should be thinking that this alkyl halide should most preferably be methyl or primary. And that alkylates the alpha position, right, to introduce an alkyl group, again, that is either a methyl or a primary alkyl group. After that alkylation reaction, we can use acid catalyzed hydrolysis, and we will hydrolyze both esters to a carboxylic acid. And recall that's a reaction from the previous chapter, chapter 20. And once we have the diacylic acid, If we just heat it up, it will undergo a decarboxylation reaction, and we will remove one of the carboxylic acids. The carbon and the two oxygens become carbon dioxide, and then the proton is just removed for transfer. So the 1,3-dicarboxylic acid can be redrawn, right, where we essentially flip this carbonyl, right, in this alcohol group. And the reason why we want to do that is because when we do that, we can more easily draw the mechanism of the decarboxylation step. Notice that it's a paracyclic reaction. We have electrons flowing in a ring-like formation, right? And we are cleaving this carbon-carbon bond to lose carbon dioxide. The intermediate that's formed is an enol. And as we know, enols under either acid or base catalyzed conditions will tautomerize to the keto form, which is the more favored form of the between the two constitutional isomers. Okay, so overall, we've used diethyl malonate and an unhindered alkyl halide to combine those to form a carboxylic acid. If we think about where the carbons come from, right, we have the carbons from the alkyl halide, shown here in black. This is our new carbon-carbon bond that we formed. And then the two carbons, right, from the carboxylic acid and the alpha carbon come from diethyl malonate. Okay, so we can also doubly alkylate diethyl malonate if we want to. So for example, we can do a series of deprotonation, alkylation, and then deprotonation, alkylation again. Right? And this will introduce two alkyl groups onto the alpha position between the two carbonyls of diethyl malonate. And at that point, if we do an acidic hydrolysis with heat, again, we will hydrolyze both esters to carboxylic acids, undergo a decarboxylation in order to achieve the carboxylic acid. In this case, the alpha position of the carboxylic acid has two alkyl groups instead of one, which might be synthetically preferable. I'm going to just pause it for a second. Recording. Okay, sorry about that. I just wanted to make sure everything was going okay with my voice. Let's go back to the presentation. Okay, so we were just talking about the malonic ester synthesis, which converts an unhindered alkyl halide to a carboxylic acid. But perhaps we want a methyl ketone instead of a carboxylic acid. We can do that with a related reaction called the acetoacetic ester synthesis. And it's so called that because we start with ethyl acetoacetate instead of malonic acid, the malonic ester. So note that the difference here is just this methyl group that is present instead of a second ethyl ester, right? So instead of starting with a diester, we're starting with a beta ketoester, which you might note is the product of a Klein condensation. Right? So this is a way to string reactions together synthetically, is to recognize when the reactant of one reaction is also the product of another reaction that we talked about. So beta ketoesters are produced Klein condensations, and then we could further react that product with a under the acetoacetic ester synthesis conditions to form a methyl ketone. The reaction again is very similar to the malonic ester synthesis. We would treat with a matched alkoxide to the ester to form the doubly stabilized enolate, will undergo an SN2 reaction with an unhindered alkyl halide. We'll then need to do an acidic hydrolysis of the ester to a carboxylic acid, followed by heat for the decarboxylation. So, and make sure that we fully understand how to utilize either the malonic ester or the acetoacetic ester synthesis. Let's go ahead and do a practice problem and think about how you would synthesize these two compounds using either of those two reactions. Go ahead and pause it and do your best, and we'll talk about it in just a moment. Okay, so let's go ahead and go over how to tackle these problems. Right, so you might have noticed that we have this methyl ketone, right? And this would be one of the two alpha carbons, right? So perhaps we could have introduced these two alkyl groups through alkylations of that alpha position. So that's something to think about, right? And if we want to make a methyl ketone, then we want to use the acetoacetic ester synthesis. And because we're introducing two alkyl groups, we're going to do the double alkylation process. So starting off, we can draw either ethyl or methyl acetoacetate. And we can do a alkylation. And again, we're going to use the matched alkoxide. And it doesn't matter which of these two alkyl groups you introduce first, but I'll go ahead and add in the methyl group first. And again, you can use methyl chloride, bromide, or iodide. I'm going to choose the best leading group, which is iodide in this case. And I'll draw the product of that step. So again, we will selectively alkylate the interior alpha carbon. In that process, we can do another alkylation. Introduce the second alkyl group. Notice that we're going to need a 3-carbon alkyl halide. This time I'm going to use alkyl bromide, but it doesn't matter. And I'm going to draw the product of that step. Okay. And then recall that the last step to get to the product is a acidic hydrolysis, right, with heat. And the acidic hydrolysis will hydrolyze the ethyl ester to a carboxylic acid, which will then decarboxylate, and we'll end up losing this entire group, replacing it with a hydrogen. So we can go ahead and draw the product. Which is this one, which is the same product as here. Okay, so we're going to do a similar analysis for the carboxylic acid. There's the alpha position, so we can think about introducing these groups through successive alkylation reactions. Because we have a carboxylic acid product, we're going to use diethyl malonate as our starting material. And again, I need to do a double alkylation because of the introduction of two different alkyl groups. Start off with sodium ethoxide. Treat this with either one. We're going to introduce our ethyl or purple first. It doesn't matter. Choosing to introduce the ethyl first, so go ahead and draw that product. sodium ethoxide again, and now propyl. Or bromide or iodide. Right? And then the last step will be the hydrolysis of the two esters and decarboxylation. We'll write H3O plus again and okay, and that's the same product then that we were trying to go for. All right, let's head back to the slides and continue on. Now we're moving to 21.6, conjugate addition reactions. So recall from earlier in the chapter, we can synthesize alpha, beta, and saturated aldehydes through aldol condensation reactions, starting from simple aldehyde. And now we're going to talk about subsequent reactions of this as a reactant that we were able to synthesize previously. Let's first start by drawing out the resonance contributors of the alpha, beta, and saturated aldehyde. We'll start with the pi bond between atoms of differing electronegativity pattern, moving electrons up to the oxygen, revealing a negatively charged oxygen and a positively charged carbon. And then you might recognize the allylic carbocation pattern, where we can shift the pi electrons over to instead be between these two carbons, and then the positive charge then moves over 2 positions. So what does this tell us? It tells us that the true structure, the oxygen has a partial negative charge through resonance, or the pi system, and it also has a partial negative charge through induction, which is through the sigma bond. And it also tells us that the carbonyl carbon has a partial positive charge. Probably knew that already. We talked about that numerous times over the last few chapters. But in addition to that, the beta carbon is also partially positively charged. And that's what this particular resonance contributor reveals. So it's not just the carbonyl carbon, also known as the ipso carbon, that has a partial positive charge, but the beta carbon as well has a partial positive charge and is electrophilic. So as a result, it can react with certain nucleophiles to give desirable products. So here is the talking about the 2 electrophilic positions. Right? Both of those have a partial positive charge. And either position could potentially be attacked to, for example, form a new bond, perhaps a new carbon-carbon bond. Depending on the nucleophile used, it's possible to prefer attack on the ipso carbon or the beta carbon. Okay, so Grignard reagents will generally attack the carbonyl carbon or the ipso carbon. Right? This is called 1,2 addition, and the counting starts on the oxygen. So this is atom number 1, and then the carbon here would be atom number 2. Right? So the why they call it a 1,2 addition is notice the product position number 1, which is the oxygen, has gained a proton. And position number 2, which is the carbonyl carbon, has gained a new carbon-carbon bond, right, in a new alkyl group. And we've talked about Gilman reagents before, right? So Grignard reagents are organomagnesium compounds, and Gilman reagents are organocopper compounds. We've talked about the difference in electronegativity between carbon and magnesium and carbon and copper previously. And we found that the difference in electronegativity between carbon and copper is much smaller than between carbon and magnesium. And what that tells us is that the carbon attached to the magnesium has a much more significant negative charge, and as a result is much stronger base and stronger nucleophile. whereas the carbon attached to the copper does not have as significant a negative charge, and as a result is a much weaker nucleophile slash base. So we can take advantage of the fact that this alkyl group is a stronger nucleophile and this alkyl group is a weaker nucleophile to utilize different reactions from our alpha beta unsaturated aldehyde reactant. So in contrast to the Grignard reagent, where it's a strong nucleophile and prefers attack at the more electrophilic alpha or ipsocarbon, the Gilman reagent will prefer what's called conjugate addition or 1,4 addition, and the new carbon-carbon bond will be formed between the incoming nucleophile and the beta carbon. And notice how the pi bond is the carbonyl in this case, and the pi bond is actually a carbon-carbon double bond or an alkene in this case. So let's talk about the terms here, 1,4 addition or conjugate addition, and where do those terms come from and what do they mean? So recall that we called the Grignard's nucleophilic attack a 1,2 addition, right, because the hydrogen got added to position number 1, which is oxygen, and the carbon nucleophile got added to carbon or position 2. Here we have the alkyl group adding to what would be position 4 if you start counting with the oxygen. So if this is 1, 2, 4, our carbon-based nucleophile is attached to carbon 4. And it might be a little bit confusing as to why this is called 1,4 when the oxygen position 1 has not changed. So we're going to have to actually look at the mechanism a little bit to understand entirely the term 1,4 addition or conjugate addition. But for now, on this slide, I just want you to recognize the use of 2 different reagents, both a stronger nucleophile and a weaker nucleophile, and their reactivity difference, specifically where that new carbon-carbon bond is formed, is at carbon 2 versus at carbon 4, or I should really say position 2 or position 4, you're starting from the oxygen position 1. And again, I'm going to talk about why these products are different as we analyze the mechanism on the next slide. Okay, so let's look at the mechanism of conjugate addition. So again, our nucleophile, which is typically going to be a weaker nucleophile, will attack at position 4. So you might be asking yourself, why doesn't it attack at position 2? Right? And the answer is it does attack at position 2. And in fact, it probably attacks at position 2 initially in greater amount than position 4. And the reason for that is because position 2 is more electrophilic. And not only does it have a partial positive charge, but it's also closer to the electronegative oxygen atom. So through induction, this carbon is just going to feel a stronger positive charge than this one. So the nucleophile, and it can be any nucleophile, strong or weak, will initially prefer to attack here at position 2. However, when you use a strong nucleophile, that nucleophilic attack is irreversible and you trap that product, and that leads to the product that we saw, for example, with the nucleophile as a Grignard reagent. But when we have a weaker nucleophile, note that weaker nucleophiles are more stable, and they also act as better leaving groups. So while we can do an initial preferential nucleophilic attack at position 2, that's reversible. And we can do a loss of a leaving group to kick it right back out. Eventually, it can also sometimes attack position 4, which, as we've talked about, is also electrophilic. When it does a nucleophilic attack on position 4, in order to avoid the octet on this carbon, we start moving electrons, and we can either deposit them as a lone pair on the alpha carbon, forming one resonance form of the enolate, or move the electrons all the way up to the oxygen to form the other resonance form of the enolate shown here. Okay, and when we do that nucleophilic attack at position 4, we end up with an intermediate that is much more stable than the one that is formed when we do a nucleophilic attack at position 2. because the intermediate involves an enolate, which is delocalized and resonance stabilized anion. And if you draw out the intermediate that forms from direct nucleophilic attack at position 2, notice that the alkoxide, or the negatively charged oxygen, is localized. And because this carbon becomes sp3, that lone pair is not delocalized with the pi bond. So that intermediate is much less stable than this intermediate. So again, nucleophilic attack will preferentially occur at the more electrophilic a carbon first. If the nucleophile is weak enough, it can also act as a leaving group and get kicked right back out. Eventually, it might do a nucleophilic attack on carbon 4, forming a more stable enolate intermediate, which can get protonated to form an enol. When you see this structure, it's much easier to understand why this is called a 1,4 addition. The hydrogen gets added temporarily on the oxygen, and again, that's position 1, and the incoming nucleophile gets added at position 4. So we've done an addition of 2 groups, one at position 1 and one at position 4, hence the term 1,4 addition. It's also called conjugate addition because of the intermediate being an enolate, which is the conjugate base of an aldehyde or ketone. Okay, so initially you can show proton transfer at the oxygen if you want to form the enol, but then of course enols tautomerize to their more stable constitutional isomer, the keto form, which in this case is an aldehyde, and overall then that proton moves from the oxygen to the alpha carbon. So in the end, the addition is really, if you start counting here, would be at position 3 and 4, but instead, because of this, call this a 1,4 addition. Okay, so just in summary, stronger nucleophiles such as the Grignard reagent tend to do 1,2 addition, right? And that's because, again, that carbon is more electrophilic, and so its initial reaction, where we're doing a nucleophilic attack, is preferred at the carbonyl carbon. And you cannot reverse that particular step because carbon anions, where they are not stabilized, right? So again, the Grignard reagent is a strong nucleophile, strong base, so it's a very poor leaving group, right? That is an irreversible step, and we cannot kick out the alkyl anion to then eventually prefer conjugate addition. So strong nucleophiles like Grignard reagents tend to just do 1,2 addition, forming that new carbon-carbon bond at the carbonyl carbon. Much weaker nucleophiles tend to do 1,4, also known as conjugate addition. And that's because while they might initially prefer 1,2 addition, that's reversible, and eventually the more stable conjugate addition wins out in terms of equilibrium. So one thing to note is that typical enolates, right, like that you might form from cyclohexanone. Imagine not having the second carbonyl here. So a typical enolate that's not doubly stabilized, but only singly stabilized with 1 oxygen. It tends to give a mixture of 1,2 and 1,4 addition products. So unfortunately, that type of enolate is not considered a strong nucleophile or a weak nucleophile, somewhere in between. And as a result, it tends to give a mixture of 1,2 and 1,4 addition products. However, if we do start out with a doubly stabilized enolate, which might be formed from this 1,3-diketone and potassium hydroxide, that is a weak enough nucleophile that it will prefer exclusive 1,4 addition or conjugate addition. And it will exclusively attack then the beta carbon, right, forming this new carbon-carbon bond you see here in this product. And that reaction is called what's known as the Michael reaction. Right? So essentially, when we use a weak nucleophile, super weak nucleophile, and do a conjugate addition or 1,4 addition on an alpha beta unsaturated substrate, that is called a Michael addition. We're going to see lots of examples of that. And again, we also need an acidic workup to avoid a substrate that's charged in the end and to isolate a neutral product. Okay, so again, conjugate or 1,4 addition is called the Michael reaction. We often talk about Michael reactions involving a Michael donor and a Michael acceptor. The Michael donor is the weak nucleophile, right, which would be the enolate formed from the deprotonation of this 1,3-diketone. That would be considered the Michael donor. And then the Michael acceptor is the alpha beta unsaturated carbonyl component, right? So for example, this alpha beta unsaturated aldehyde, we would call this the Michael acceptor. And those together, right, form this carbon-carbon bond. There's a table in your book that talks about a list of common Michael donors and Michael acceptors. So remember, we noted that Michael donors are weaker nucleophiles. So for example, anything that's doubly stabilized in terms of an enolate would be considered a Michael donor because it's a much weaker nucleophile. The alpha position to a nitro group is considered a weaker nucleophile because this anion is well stabilized through the nitro groups, through resonance and through induction. And also Gilman reagents. Right? These are a little bit different from the other examples here, right? But they're considered weak nucleophiles. And so they do exclusive conjugate addition. So we're going to call them a good Michael donor. Notice that Michael acceptors are alpha beta unsaturated carbonyl containing components most of the time. A couple of exceptions here, but the very similar nitrile group, right? There's a pi bond. There's actually 2 pi bonds between the carbon and nitrogen, but one of them is in conjugation with this pi bond and can substitute for a carbonyl. And then also there's a nitrogen oxygen double bond that can substitute for a carbonyl. So these are all good Michael acceptors. And they will react together to do conjugate addition or 1,4 addition. And I actually wanted to, and I forgot to do that, just take a look at the product a little bit. We want to think about the relative relationship of the functional groups, right? So if you think about maybe calling this carbon number 1 or position number 1. We start here 1, 2, 3, 4, 5, right? 4, 5. So we have a carbonyl at position 5 and position 1, right? And the second carbonyl also at a second position 5. So, but we want to think about the fact that we have a 1,5 dicarbonyl system, right? Or tricarbonyl system. So, and the reason why it's important to think about how you classify the product is because you want to look at the functional groups in the product in a synthesis problem and ask yourself, what reaction should I use? And in this chapter, there's a lot of new carbon-carbon bond forming reactions. So it can be a little bit confusing figuring out which one to use. So the more we can classify the different types of products in terms of their relative positioning functional groups, the easier synthesis will be for us. So we'll be able to hone in on which reaction produces that sort of functionality. Okay, let's go ahead and do a practice problem. And we are going to, we're being asked to identify reagents that can be used to achieve the following transformation. Right, and the double arrows here signifies that we're doing a multi-step synthesis. Right? So, of course, you want to think about the fact that the carbon backbone has changed here, right? To think about what reaction you might use, and think about how you might achieve this synthesis. And go ahead and pause it and do your best You might even come up with more than one possibility and then choose your favorite, and then we'll talk about it. Okay, so let's go ahead and go over this problem. So I want to go ahead and talk about some possibilities, just because you might have thought of some things that maybe wouldn't work, and I want to kind of talk about why they wouldn't work. So you're probably analyze this to realize that we need to make this carbon-carbon bond. That's going to be important. And because this is an alpha carbon, right, you might be thinking, well, maybe I can just do an alkylation of the alpha position. But recall that because that relies on an SN2 reaction, we most preferably need to add in either methyl or primary alpha groups. And this would be the addition of a secondary alkyl halide, which again will not happen in good yield. Instead, elimination will be dominant over substitution. So we do not want to do an alkylation of the alpha carbon. So I just wanted to point that out in case you were thinking that. It's not a bad reaction to think of, but it just wouldn't be useful in this particular case. Okay, so another thing you might be thinking of is, well, how can we potentially introduce this, right? Maybe we can have achieved this product through some sort of conjugate addition. And if we were doing a conjugate addition, we would need a double bond here, right? Because the reactant for a conjugate addition is an alpha beta unsaturated carbonyl. Okay, so perhaps we might think about introducing this R group via conjugate addition. So if that's the case, then we might target perhaps this alpha beta unsaturated aldehyde as our key synthetic intermediate. Okay, so then we might think about, okay, how can we make that and how can we use that to make the product? So recall that alpha beta unsaturated aldehydes are made through aldol condensation reactions. So we need to do, in this case, we're going to want to do an aldol condensation. It's always good to think about the reaction that you're going to be using, because it helps you come up with the correct reagents and focus on the reaction of choice. Okay, so if we think about the two, right? So the aldol condensation would utilize two aldehydes, right? And we would be making this carbon-carbon double bond. And to go backwards retrosynthetically, which is always helpful, is to think about the two aldehydes that would be used in that aldol condensation. So in one case, we would have the enolate, right? And in the second case, wherever that carbon-carbon double bond is, we'll go ahead and add a carbonyl, and whatever is attached here will be attached to that carbonyl. So there'll be a hydrogen and a methyl group. So perhaps you recognize the fact that these are actually coming from the same aldehyde. Right? So we just need to do a typical aldol condensation where we're dimerizing the same aldehyde. So no need for a crossed aldol condensation. So just starting from two equivalents of this, right, with an appropriate strong base, such as sodium hydroxide, we can do an aldol addition. And if we want it to go all the way to the condensation, we should also add heat. That will give us this alpha beta unsaturated aldehyde product, which is a good substrate for a conjugate addition or addition. Notice that if we want to add just a typical alkyl group through conjugate addition, our nucleophile needs to be a Gilman reagent. So we're going to use a Gilman reagent where our group is a methyl group. That will be the appropriate Gilman reagent to just introduce. Okay, let's go ahead and head back to the slides. On. The next reaction in this section of the book is called the Stork-Enamine synthesis. So Gilbert Stork actually developed this synthesis to avoid the problem of not being able to utilize a typical enolate in a Michael addition. So recall that if we were to use this ketone to form an enolate, the stability of that enolate is intermediate. It's not considered a strong nucleophile, and it's also not considered a weak nucleophile. So it would give a mixture of 1,2 and 1,4 addition products through when treated with an appropriate alpha beta unsaturated acceptor, right, like you might see in the Michael acceptor. So what he did was he realized that instead of using a typical enolate through deprotonating the ketone, what if we then converted that same ketone to an enamine? So recall we talked about enamines back in chapter 19, section 6 of that particular chapter. And we form them through the condensation of ketones or aldehydes and secondary amines. Right? It is an acid catalyzed reaction, and it's equilibrium based, so we need to remove water as a product or add excess of one of the reagents to get a good yield of the enamine product. When you analyze the resonance contributors of an enamine and compare it to an enolate, you'll see some definite similarities. Right? The alpha carbon is has a partial negative charge in both cases, which means that they're both going to be nucleophilic at this carbon. There is some differences though, right? Because we have a full negative charge with an enolate ion, this is a stronger nucleophile than an enamine. While we do have a partial negative charge on this carbon, right, there isn't a full negative charge overall. This is neutral overall and much more stable. And as a result of it being more stable, it's a weaker nucleophile than an enolate. It's actually more, its nucleophilicity is more in par or on par with an enol than an enolate. But a enamine is a terrific then Michael donor because it's a much more stable nucleophile compared to an enolate. So recall an enolate is just a little bit too nucleophilic to exclusively do conjugate addition, leading to a mixture of products. But enamines are more stable and less nucleophilic, right? So they are terrific Michael donors. You can then treat it with an appropriate Michael acceptor to do the Michael addition reaction. So what I would recommend you do is go back to slide number 83 and that table where it lists Michael donors and Michael acceptors, some common ones, and go ahead and add in the enamine to the Michael donor list, right? Because enamines are also good Michael donors. It wasn't included in that particular table in your book because they talk about it after that table is introduced, but it is a good Michael donor. So go ahead and add that to your notes so that you have that all together. So after we do the conjugate addition, also known as the Michael addition, to form this new carbon-carbon bond, we end up with an enolate and an iminium ion. So we do need to stir it around with some catalytic acid. What that will do is both protonate the enolate and give us the neutral ketone, and also hydrolyze the iminium ion back to a carbonyl. So we're able to make this carbon-carbon bond without having a doubly stabilized enolate as our nucleophile. Instead, it's only one carbonyl is present, not two, right? When we convert the ketone first to an enamine. Notice the product is what we might call a 1,5-dicarbonyl. I just say dicarbonyl to keep it more general, right? But in this case, technically a diketone product. And again, keeping the relative positioning of these functional groups in mind is going to be important in tackling synthesis problems in this chapter. Okay, so overall, the stored enamine synthesis is a three-part process. We start with a aldehyde or ketone, form an enamine, and then treat the enamine with an appropriate Michael acceptor, followed by an acidic hydrolysis, and we'll get a 1,5-dicarbonyl product. Okay, let's take a break and do a practice problem. Right, so this problem asks you to utilize a stored enamine reaction and show how you might synthesize the following compound. Right, so you just need to make this through some sort of stored enamine synthesis. Okay, so go ahead and think about the positioning of your functional groups, what carbon-carbon bond you want to synthesize using this reaction, and simplify that through retrosynthetic analysis to reactants. Okay, go ahead and pause and then. Okay, let's go ahead and go over this practice problem. Okay, so we talked about looking at the positioning of the functional groups. We have a carbonyl here at what you might call 1, 2, 3, 4, 5, or 1, 2, 3, 4, 5. Either way, we have a 1,5-dicarbonyl product. So and because I don't have a third carbonyl or equivalent electron withdrawing group, I'm not thinking about using the classic Michael reaction. Instead, I need to use a stored enamine reaction to make this product. So when you're counting the carbons, right, 1, 2, 3, 4, 5, or 1, 2, 3, 4, 5, we're going to be making the bond between carbon 3 and 4. So if I was to count this direction, right, then my carbon-carbon bond that I'm going to be making is this particular carbon-carbon bond. If I had counted starting over here, I would make this particular carbon-carbon bond. So there are some choices here that you have in which exact stored enamine synthesis reaction you want to use. I think it is easier to utilize the green pathway and make this carbon-carbon bond, just because that leaves this as an intact ring. If I end up making this carbon-carbon bond, then I need to rely on making a ring in my reaction and doing an intramolecular reaction, which is possible, but perhaps not quite as easy as making this. So we can then retrosynthetically, sort of highlighting this, right? We're going to sort of break it into two pieces. And on one side, we're going to have the enolate, and the other side will be one side needs to be the Michael donor, and the other side needs to be the Michael acceptor. Okay? And so if you're counting this direction, then the piece on the right is the Michael acceptor. So this would be a double bond here. Okay, so this piece is going to label it as our Michael acceptor. And then this piece will be our Michael donor. Okay? And again, it's would just be a typical enolate, which doesn't work in Michael reactions, so you need to convert that into enamine. Okay, so then that simplifies to perhaps utilizing this enamine, some sort of enamine. It doesn't have to be a ring here, but it's a common type of enamine to form. So go ahead and use that one. And then the Michael acceptor needs to have the double bond between, in this case, it would be labeled carbon 2 and 3. So it needs to be an alpha beta unsaturated carbonyl. Okay, so this then helps us with the forward direction synthesis. I know I need to make this enamine, add this Michael acceptor, and do an acidic hydrolysis. It's a 3-part synthesis. So simplifying that enamine down to a ketone, we end up with pentanone. And we're going to do our 3 steps to form the product. So the first step is going to be formation of the enamine with a secondary amine. So I chose to use bromidine as my secondary amine. And you could use other secondary amines though, it doesn't matter. And again, this is typically an acid catalyzed reaction that we drive the water out of to favor the equilibrium of the product. The second step will be the Michael addition step. So we throw in the Michael acceptor. And we need, in order to hydrolyze the iminium ion and protonate the resulting enolate, we need a acidic hydrolysis at the end, right? And this will give us the product as the desired product. Okay. Let's head back to the presentation. Okay, next we're going to talk about what's called the Robinson annulation reaction. It is a ring-forming reaction, and it specifically utilizes 2 reactions that we've talked about previously. A Michael addition followed by an aldol condensation. So it is a multi-step process that can happen all in one pot. The first reagent is just sodium hydroxide. That will give us the Michael addition product. But if we heat that product, it will further react to do an aldol condensation reaction, specifically between this, the enolate formed from this ketone and this carbonyl, leading to an alpha beta unsaturated ketone over here. Right? So the mechanism will really involve reactions that we've already talked about, like the Michael addition and the aldol condensation. So it's going to challenge you to think about drawing the mechanism. Recall that it's under basic conditions, right? So we do need to draw a mechanism consistent with basic conditions. And it utilizes, again, right, make sure to do that full Michael addition followed by the aldol condensation. And because it's a condensation, we expel a small molecule, right? So in the end, produce water as a product. Actually, kick out hydroxide, which can get proteinated. Okay, so I would like you guys to think about and practice drawing a reasonable mechanism for this reaction. So without me going over it first, see if you can figure out how to start from this Michael donor and this Michael acceptor to first do a Michael addition followed by an aldol. So go ahead and pause the video, and then we will talk about it. Okay, so let's go ahead and go over this. So we have, we're going to first start out with our Michael addition. And again, that's going to involve forming an enolate first, the base that's used, followed by a conjugate or 1,4 addition. So I'm going to go ahead and draw in the hydrogen that's present on that alpha carbon between those 2 carbonyls, and then some hydroxide, which is added as the reagent. And we'll do a proton transfer to form our doubly stabilized enolate. So again, you can form an enolate and draw either resonance contributor that you want. Right? Sometimes it's simpler to just put the lone pair and negative charge on the alpha. We can start off forming the enolate. And then I'm just going to move this down so it's closer. Now I'm going to do the conjugate addition, also known as 1,4 addition, where we do nucleophilic attack on the beta carbon of this particular alpha, beta unsaturated ketone. Again, to move the electrons away from this carbon, I'm going to move this pi bond. I can either deposit it on this carbon as a lone pair, negative charge, or I can move the electrons all the way up to the oxygen. It's up to you. Okay. I am just going to deposit it on the alpha carbon. Can be tricky when you're making a new carbon-carbon bond between two things, but you can see that this methyl is drawn up here, so we're going to just go ahead and sort of move that methyl up here, and then draw the new carbon-carbon bond, and then keep going. Right? So this one has the lone pair and the negative charge, and then add in the okay, so we ended up with this enolate. So you might be thinking, okay, at this point I can do a nucleophilic attack, but this would be a 1, 2, 3, 4. This would be a 4-membered ring that formed if we just do a direct nucleophilic attack on that carbonyl. Recall that 4-membered rings have a lot of ring strength, so it is not ideal to form a 4-membered ring. So what we're going to do is a proton transfer sequence, where we protonate this alpha carbon and then deprotonate the other alpha carbon with this ketone. The reason for that is once I have the lone pair and negative charge on this alpha carbon, doing a nucleophilic attack will form a 6-membered ring, which is much more favorable compared to a 4-membered ring. So my goal then is to protonate here and then deprotonate there. Recall, I don't do it in the opposite order, because we want to avoid forming any intermediates with more than one negative charge. That would be too unstable. So it's much more likely that we first get to a neutral intermediate and then deprotonate the other alpha carbon to get to an intermediate with one negative charge. So under basic conditions, we have sodium hydroxide and we also have water. So water is the acid that's present in solution under basic conditions. So don't use hydronium ion because there is no hydronium ion present in this reaction. So we're going to transfer from water, again allowing us to get a neutral. Intermediate, and then we're going to deprotonate the other alpha proton. So I'm going to deprotonate with hydroxide as a base, and go ahead and add in some hydroxide to deprotonate. I'm going to deliver the lone pair to the alpha carbon. We have the enolate, which now we can do a nucleophilic attack to form a 6-membered ring. Much more favorable than forming a 4-membered ring. It can be tricky forming rings, right? So if you want to, feel free to number carbons so that you can keep track of them. but it's also useful to just look at this as sort of a template of how it's going to look once we form that second. Okay, so the first couple of steps were the Michael addition, and then starting here, we're starting to do the aldol condensation. Enolate, do a nucleophilic attack. We end up with this negatively charged oxygen, which will be protonated with water to give the beta hydroxy keto product that you would get from an aldol addition reaction, and then we'll go on to do the condensation part of the aldol reaction. I'm going to go ahead and draw in some water, show proton transfer. Okay, and now we're ready to do the condensation part. We'll call that the condensation reaction. Aldol reaction is an E1CB mechanism. So we need to do this over 2 steps, where we first deprotonate the alpha position between the newly formed hydroxyl group, or alcohol, and carbonyl to generate the conjugate base, which then does the elimination. Now that we have formed it's called the conjugate base, we'll do the E1CB reaction, where we do a elimination from the conjugate base. So we're forming this pi bond, the alkene, and kicking out hydroxide. This is the step that generates the product. And also got some hydroxide. Okay, so there's the overall mechanism. We will back to the slides. Okay, so we're moving on to 21.7, which discusses different synthesis strategies for this chapter. So it's important to recognize that a lot of the reactions in the chapter involve new carbon-carbon bond forming reactions. And the products contain at least 2 functional groups, right? So some reactions, right, that we learned are, for example, the aldol reaction or condensation, the Klein condensation or the Stork-enamine synthesis, and ask yourself, what sort of products are formed here? How do we classify those? What do we call them? What functional groups are present? What is their relative positioning? And how do I know if I'm going to be using that reaction or a different reaction when I'm doing these problems? So for example, if you're doing the Stork-enamine synthesis, we end up with a 1,5-dicarbonyl. If you're doing an aldol reaction, you end up with 1,3-difunctionalized compound, but more specifically a beta-hydroxyaldehyde or ketone. If you're doing a Klein reaction, we end up with a beta-ketoester, right? So the relative positioning of the functional groups and exactly what the functional groups are will help us figure out which reactions to use in this chapter. Recall that we have learned how to do a couple of different alkylation reactions in this chapter. We can alkylate the alpha position of an enolate using an SN2 reaction with an alkyl halide. And we can also do Michael reactions. Right? Michael reactions also involve the alkylation of the alpha position, but specifically we end up doing conjugate addition or the nucleophilic attack. Instead of on an alkyl halide, it's on what's called a Michael acceptor, and specifically the beta position of the Michael acceptor. These two reactions can also be combined into one single reaction. So notice that this would be like alkylation at the alpha position, and this is alkylation at the beta position. So the introduction of this ethyl group had to occur using a Michael reaction, and the introduction of the methyl group then occurred from a simple alkylation of the alpha position. Which one would we do first? Well, if we start from an alpha beta unsaturated ketone, this is the starting material for a Michael addition. So we'll do a Michael addition with a Gilman reagent first to introduce this ethyl group. The initial product is an enolate, which if you don't add acid but instead add methyl iodide, the enolate can be directly alkylated to introduce a methyl group. So that's a way to introduce two new carbon-carbon bonds in one reaction by sequencing a Michael addition followed by the alkylation of an enolate at the alpha position. Let's do some practice problems. We're going to do 2 practice synthesis problems, and you can do many more practice problems in your book as well, and I highly recommend that you do that. Okay, so the first one says our goal is to synthesize this compound starting with anything that we want, as long as it contains 5 carbons or less. So go ahead and think about how you could break this up into chunks where no reactant contains more than 5 carbons, make a new carbon-carbon bond in that process, and which, based on the relative positioning of the functional groups, think about what reaction you might want to choose. So go ahead and pause this and try, and then okay, so let's go through this problem. So it might look initially like this doesn't belong in this chapter, right? I don't remember seeing the formation of a diol specifically, like if I was to start counting here, I had a 1,5 diol. I don't recall any reactions that produced a 1,5 diol. However, I do recall reactions that produced a 1,5 dicarbonyl. Right? And just remember that alcohols and carbonyl compounds are related through redox reactions. So perhaps if I think about the fact that this might have come from a 1,5 dicarbonyl, I can think about instead convert that secondary alcohol to a ketone and convert the primary alcohol, carbon 1, to an aldehyde. So all I have done is essentially an oxidation. Retrosynthetically, or in the forward direction, it would be a reduction. But now I have my relative positioning of my 2 functional groups as 1,5. Right? So this is a 1,5 di-functionalized compound. And it is their 2 carbonyls, which is something that we know how to make through the Stork-Enamine reaction. Okay, but I still haven't broken this up to 5 carbons or less in terms of the reactants. But recall that I can make 1,5 dicarbonyl compounds through Michael addition reactions. And I'm going to make either the bond between 2 and 3 or 3 and 4, depending on how I counted it. So to me, it makes sense to just make the bond between 3 and 4 that leaves this as the enolate, and then we can utilize this as the Michael acceptor, right? So the donor and the Michael acceptor. One of the reasons why I didn't break it between 2 and 3 is because of the instructions, right? 5 carbons or less. If I had broken and made the bond between carbon 2 and 3, this piece would end up having 6 carbons, and I would have to make that, which just makes more work for me in terms of the synthesis. Because then I have to make that 6 carbon thing with 5 carbons or less. Okay, but this breaks it into chunks of 5 carbons or less directly. So synthetically, it'll be a faster synthesis to do it this way. Okay, so then if this is going to be made through a Michael reaction, specifically the stoichionamine version of the Michael reaction, right, then that means I am going to go back to an enamine, right, and a Michael acceptor, which in this case will be an alpha beta unsaturated aldehyde. Okay, so that's my general retrosynthetic analysis. And then in the forward direction, I can start by making the enamine. So I'm going to take cyclopentanone, first form an enamine, rhodine, then I'm going to add in the Michael acceptor of my choice, which is going to be this one. Followed by an acidic hydrolysis step. So remember, the stoichionamine synthesis is a 3-step process. That is going to, in one step, go ahead and yield me my 1,5-dicarbonyl intermediate that I had determined I wanted to make prior. Okay, and then again, we can just reduce these 2 carbonyls using either sodium borohydride or lithium aluminum hydride. So you can basically say excess sodium borohydride, right, or excess LAH. And that will give us the product. Okay, let's move on to the next practice problem. This one is another synthesis, and we're going to look at the directions for the problem. Using 1-propanol as your only source of carbon, synthesize the following compound. So that means that you have to start with 1-propanol. You cannot get carbons from any other source. If you're looking at this, this contains 6 carbons, so we're probably going to incorporate 2 propanols in the synthesis. Again, look at the relative positioning of the functional groups. Think about what you could have made those functional groups from in order to aid you in trying to figure out how to synthesize this product. So go ahead and pause it. Best. We'll talk about it shortly. Okay, so go ahead and we're going to go ahead and go over this problem. Okay, so if I'm thinking about counting, then I can start here or here. If I start here, then it's 1, 2, 3. Right, so we have a 1,3 difunctionalized product. Okay. I don't recall making a 1,3 diol in any reactions. However, of course, I could have gotten one of these alcohols or both from reduction of a carbonyl. If we end up oxidizing both of them, this one will oxidize to an aldehyde, right, because primary alcohols oxidize to aldehydes, and the secondary alcohol would oxidize to a ketone. So if you want to think about that, we certainly can do that. Okay. I end up oxidizing both of them. I would get here. Maybe I think about only oxidizing one of them. Right? That gives me, which of course in the opposite direction will be a reduction. and oxidize the primary alcohol. Or I can also consider oxidizing only the secondary alcohol. So perhaps one of these will lead me then to this through a reduction. So you want to ask yourself, which of these is the easiest to make? Which of these is the easiest to make? If you think about the fact that this is a beta hydroxy aldehyde, right? We know we can make this through a aldol addition reaction. So that's one possibility. The other possibility is this right now is a beta keto aldehyde, which I don't know how to make, but if this was an ester, then I could have, this would be a beta keto ester, right? And I could have possibly utilized a Klein condensation. Right? So that seems like more work to me, right? Because I can directly make this one through an aldol, but it is possible to convert propanol to an ester. First, you would oxidize it to a carboxylic acid, convert it to an ester through one of your ester forming reactions. There are 3 choices from the last chapter. And then you could do a Klein condensation, but it's going to be a difficult battle then to reduce, to do the reduction. Or you don't actually have to get the aldehyde, you could just reduce the ester and the ketone together to do that. So we can actually, we can do 2 answers to this. I think the preferred answer, easier answer would be through the aldol, but perhaps you might think, okay, well, I can't, if this was an ester, right, maybe I could have made this. So we're going to kind of think about utilizing that. This one, where you have a ketone here and the alcohol here, you could think about perhaps using an aldol reaction. But it's going to be a challenge to make this particular one. You would end up, instead of making this bond, you end up making this bond. So you would have to use formaldehyde as your electrophile. And then this as the enolate forming reaction, it would be a crossed aldol reaction. If you do it this way, whereas you could just do a regular aldol reaction for this one, because this is essentially utilizing 2 equivalents of the same aldehyde. So again, we can talk about this one as well. I think it's not as preferred, but it's a reaction sequence. Okay, let's look at these. I'm going to go for this one. You're looking at these as alternate options for comparison. Okay, so the goal then would be making this particular aldol addition product. Again, if you think about the fact that this propanol and this came from propanol, right, then you just do a typical aldol where we dimerize the same aldehyde. But it told me I had to start from 1 propanol, right? So I'm going to go ahead and draw 1 propanol, make sure to show the oxidation of that to an aldehyde, so I can do the aldol addition reaction. So again, to oxidize a primary alcohol to an aldehyde, I can use PCC, right? And then we can, from here, we can do a aldol addition reaction. So we're going to dimerize or use 2 of these to produce the product. Classic aldol reactions, just use sodium hydroxide as the reagent. That is going to produce the beta hydroxy aldehyde product. And from here, I just need to reduce this aldehyde to a primary alcohol to finalize the synthesis. So a reduction of an aldehyde to primary alcohol, you can use sodium borohydride or lithium. Okay, so that's option number 1. Okay, perhaps we might think about making this beta ketoester through a Klein condensation is another option. So again, I have to start with propanol, and I need to convert it to an ester in order to do the Klein condensation reaction. So in order to convert it to an ester, I first need to oxidize to a carboxylic acid. And then from the carboxylic acid, I can produce an ester. An ethyl ester. And then from the ester, I can do the Klein condensation reaction. And that will produce a beta keto ester product. And from there, I could potentially reduce this to the product. So I can reduce the ketone to a secondary alcohol. And I can reduce an ester all the way down to a primary alcohol. Okay, so that is option number 2. Let's go ahead and add in the reagents for that. So oxidation of a primary alcohol to carboxylic acid. You need excess sodium bichromate. To convert a carboxylic acid to an ester, that was done over in the previous chapter. There's 2 ways to do it. You either use sodium hydroxide followed by a unhindered alkyl halide, which is ethyl bromide. Or alternately, you could do the Fischer esterification, which would utilize ethanol because we're making an ethyl ester and an acid catalyst. And then the Klein condensation uses the matched alkoxide. So we would do step 1, sodium ethoxide. And it would dimerize, and we would need an acidic workup in order to get the neutral beta keto ester product. And reduction of a ketone to a secondary alcohol can be accomplished with sodium borohydride or lithium aluminum hydride. However, to reduce an ester, we need lithium aluminum hydride. So it's best to just use excess lithium aluminum hydride in order to reduce both the ketone and the ester. Okay, so how about option number 3? Technically, that's a possibility as well. Might work. And so for this one, we're going to be trying to do a crossed aldol. You know, actually, I think I am just going to skip this one just because I realized, while it's certainly possible to make this, from 1 propanol, it's going to be a good amount of work. Well, okay, I'll just go ahead and why not? It's good to look at extra practice problems. Probably going to be more steps, but that's okay. So starting from 1 propanol, we need to figure out how to make this ketone, which will then convert to an enolate in the crossed aldol reaction. So in order to make a ketone from an alcohol, we can convert the alcohol to an aldehyde and then do a Grignard reaction. So the Grignard reaction will make the new carbon-carbon bond, which I can then oxidize the alcohol to the ketone. Okay, so let's go ahead and start adding in some reagents before we move on any further in this option. So to oxidize a primary alcohol to an aldehyde, we'll use PCC. Then we will introduce an ethyl Grignard. So we're going to use ethyl bromide in order to make this carbon-carbon bond. An acidic workup or water to quench the Grignard reaction. That will produce the pentanol, and from there we can oxidize that secondary alcohol to a ketone using PCC or sodium dichromate. Okay, so we were able to make this ketone, which we then can utilize to do a crossed aldol reaction. Because we're using crossed aldol, we need to carefully consider our options here. One of the great things about this particular crossed aldol is the fact that we're going to be using formaldehyde as the second component. And formaldehyde is a good choice as electrophile in a crossed aldol condensation because it doesn't have any alpha protons. So it doesn't have any alpha carbons, in fact, to have any protons attached to them. So it cannot form an enolate, which makes it easier to work with in terms of a crossed aldol condition. So we can either use LDA as the base before introducing the aldehyde, or we could even get away with utilizing a weaker base like sodium hydroxide, because again, we can only form, this is symmetrical, so there's only one possible enolate formation that can occur. And in addition, it's a ketone, so those don't tend to do great aldol addition reactions with another ketone, so the dimerization is unlikely. And if we have a very electrophilic component in there, it will likely react with the more the better electrophile, which is formaldehyde in preference to this ketone. So we could actually just use a weaker base. And that would produce the aldol addition product. Right? And to get to the product, then we just need to reduce the ketone to a secondary alcohol. And because it's just a ketone, reduction of ketone, sodium borohydride is okay. And use hydride. Okay, so that's option number 3 for synthesis here. So hopefully you came up with one of those. If you ended up with something slightly different than that, you can always submit it to me, and I will be happy to look at it and let you know if that would work as well. Okay, so that is pretty much the end of the presentation. I'll go back to the slides really briefly just to show that at the end of these particular PowerPoint slides, I went ahead and included some pictures of the reactions, just so that you can utilize these to help you make your flashcards, because there's a lot of reactions to know in this chapter, and we want to learn those as quickly as possible, and then start practicing mechanisms and synthesis for those steps. So we have alpha halogenation, right, of ketones, of carboxylic acids using the Hell-Bohar-Zelinsky reaction. We have the haloform reaction, which converts a methyl ketone to a carboxylic acid. Aldol addition reaction and aldol condensation reaction, and also the intramolecular aldol condensation reaction. An example of a crossed aldol condensation reaction. Next in the chapter, we covered Klein condensations, which produce, again, beta ketoesters. There are ways to successfully do crossed Klein condensations that were talked about. That's one example. And also the Diekmann cyclization, which is intramolecular Klein condensation. Alkylation of the alpha position. So we talked about using LDA versus sodium hydride and alkylating through either the kinetic or the thermodynamic enolate. We talked about the formation of carboxylic acids and methyl ketones using either the malonic ester or acetoacetic ester synthesis. We talked about Michael additions, which are conjugate additions to alpha, beta, and saturated carbonyl containing components. And the Stork-Enamine variation on the Michael reaction, and also the Robinson annulation, which is a Michael addition followed by an aldol condensation. Okay, so happy studying, and I hope to see you guys in office hours.